But you couldn't remember what is your question.
I was wondering why we had a clock on the after that second inversion.
Good, good. You made it. Extra credits.
I actually paid attention in this class. So.
Double here.
Everything sticks except for the tree diagrams.
Tree diagrams. Binary trees.
Like a stick diagram, but bigger.
It's the reason they added another transmission gate is to block the output from this inverter from the direct connection to here. You can imagine why it doesn't matter for this one. Why it doesn't matter? So why it's blocking this guy but not trying to block this guy? This guy has a direct connection to the transmission gate or the input, right? So this is nothing but just a switch, right? Just a switch, right? Why do they want to block this one but not this one? You have to think about the internal circuit. So that's why it's important to know the internal circuits of all the gates. For this guy, if I draw it in the same direction, it is like this. Right? That's an inverter. In that direction, the same direction. So this one, if you don't block it, whenever you are trying to give a 0 or 1 here, it's going to directly make a short circuit to the VDD. For example, you want to ground it, but this one was at VDD, for example. It's making a short circuit. But why this one doesn't matter? Because these are gates. Right? It's a gate. There's no short circuit for the DC voltage. So the reason you want to turn it off whenever it's sending data here, so you can see the clock is opposite, right? So whenever this is on, this is off. Because you can see the bar here. Okay. So whenever this is on, D will be passed to here, but this is off. You want to keep it off. Otherwise, it's going to compete with this. It's going to compete with this one. So one is pulling down to ground, one is pulling up. So which one is working here? It's shorting VDD to ground. But if you turn it off, what's happening? If you turn it off, you block these ones, any pass to here, or you are making this point or this wire, what? Yeah, floating ground or floating VDD. So only have a finite amount of charges, so you can discharge or charge it up easily by the source here. So what is the source here? Is this a finite or infinite? Is it strong logic? Yeah. It must be output from something, right? Any gates. The output of any gates are strong, being put up or being put down to ground. It's not the input, it's output. So that's why this is strong. So you have a floating voltage here, it's going to easily toggle it or keep it. So that's why you have to block it from here. So this is a D latch. It's not a flip-flop yet, it's a D latch. And you can form a D flip-flop by using another one of it, just adding 2 here. Oh, I had drawing everything. Yeah, just duplicate it. And this is Q or Q naught. If this is D. No, 2 inverters, so it's Q, right? That's D. D, invert. So it's Q. So here's Q naught, right? And you want to keep this one, I label as clock not, but you can label as clock as well, but just keep these 2 clock at the same cycle.
this SRAM go on the Q on the top? Wouldn't it invert it? No, on the, not the, on the last.
Oh, here?
Yeah. That'd be Q now.
Would be Q not and Q on top.
Yeah, right. That's right. Yeah, this is Q naught. This is Q. That's right. Thank you. Yeah. So these two are the same cycle. So this must be clock. Right, and these two are same cycle. So this is clock. This is clock naught. Okay, so definitely this is D flip-flop. It is sending D over, right? So first, this is a D flip-flop. Second, edge triggered or level triggered? And which edge? So actually, to answer that question, when you answer like when you are looking at, when you are judging if this is a rising edge or falling edge, I think you should like look at the output, not the sampling, but the output. Yeah. So when the output triggers, for example, this one, right? You can see it's a clock, not clock bar, right? So it should be rising edge triggered. Falling edge samples. See, falling edge is a sample D to here, and then falling edge will, no, rising edge will send it over here. So these two are at the same cycle, at same phase, and these two are at the same phase. So think about it, how this works. When rising edge arrives, or when falling edge arrives, D pass to here and here. There's no switch, it's just the inverter, right? It's going to pass to here. But this is blocked, okay? So whenever falling edge and 0, data will pass, right? Data passes to here. But whenever it's a rising edge and 1, it's send the data to here. But what's these two doing here? What are these two doing? So when you open up this one, when you open up these two transmission gates, are the same phase, right? So when these two are open in the same cycle, when these two are open, it samples and also stores. But it's not affecting Q and Q naught. It just stores it here as a memory. Or can say falling edge or 0, right? It passes data here, and also it stores the previous data here. Because this one is going to be off or on. Yeah, close. But previously, before it closes, there will be a data here, will be stored here when is at falling edge or 0. And when the rising edge arrives, these two are on. It's blocking any changes from D. This one will be off. And it's going to store the data here. At the same time, send it over to here. So rising edge and 1, it, what did I say here? Rising 1, it update Q. Is that correct? Rising edge and 1, or at the rising edge, it's going to update Q, and at 1, it's going to keep it there. Because these two are on, but these two are off, right? But falling edge and 0 is samples and stores. Let's use samples and stores. D. It's not holding. You need a It's the same. So you can say it's holding, right? This is a latch, right? The latch holds value. Okay. So whenever this is off, this is on, right? Remember, whenever you cut, like what I said last time on Monday, we're talking about the inverter, right? So if you open the switch, the inverter is not able to store anything. But if you have a latch, you know, previously it's feeding a signal to it, but after you open the switch, it is still having either 0 or 1 on one side, right? The latch stores it, but the inverter couldn't store anything. That's why we are using a latch here. Yeah, this is holding a value or stores the value. Yeah, only 1 zeros, right? Yeah, good point.
Okay, so the rising edge, falling edge is the clock cycle.
Yeah.
It must be 0 and 1.
Yes.
No, it's the clock, when the clock is low.
Falling in 0.
Falling in 0.
Okay.
Yeah, falling edge at 0, right? Because after falling edge, it's going to be a 0 volt, 0 volts.
Yeah.
Is this asynchronous or synchronous? Yeah,
Is it possible to have the edge trigger synchronous?
that's the ones we introduced. So you guys,
Oh,
did
yeah,
that,
that's
right?
right.
That's why we use these two ones, but not these ones. These are on the textbook. They're textbook difficult. Oh, this, yes, way less transistors. How many? Oh, 8 times 2, 16, right? Yeah. But the one we used, so the PMOS NMOS version we used, how many are there? Remember, did you count it?
Oh,
Yes, I think it's similar number.
more.
A little bit more. Yeah, but we prefer that synchronous rising edge triggered or falling edge triggered, right? It's very accurate. It only samples at the edge, and then, but this one, whenever it's open, it's gonna keep sampling, which is bad. You want to only sample at the edge because the signal can change really quickly, right? When you want to sample it, just sample it. You don't want to make any changes to the sample data.
So in order to have an edge trigger, you have to have 2 different, like you have to have a clock and a,
that's asynchronous, right?
right.
But the ones we are going to use, the 2 different versions, these are synchronous, edge triggered, which is awesome. Just sample, done. So whatever D changes, it's not going to affect anything. Okay, so you will be able to work on something similar to that later, but so 2 models for the time delay models for the transmission gates. If I have 1, 2, 3, 4, and that's a C load, CL. This is transmission gates. How to model it? Calculate the time delays. So if you look at the point here, what's the time delay at here, right? So we have 1 cap here, 1 cap here, 1 cap here, and 1 cap here. So you have mirror effect? No, there's no mirror effect. It's a transmission gate. Charging, discharging. The other side doesn't have a power connection. No VDD, no ground. So it's just either charging up or discharge it. Okay. So these are what? A half, right? Cox P. And this is also a half Cox P, right? And this is a half of Cox N. So what's the C total? Yeah. So know the capacitance. What about the resistance? So if you draw RC model. CL. So these are the C totals. Four transmission gates, so we got 4 coxswain plus cox piece here. And since 4 transmission gates, and these are, whenever the transmission gate is on, you got both NMOS and PMOS are passing that signal. So what's the resistance here? Right? You want them to be both on because PMOS is good at passing VDD and NMOS is good at passing 0, right? Whenever the transmission gates are on, you want to, both of the NMOS and PMOS are on, so you can pass the signal through. You're not turning one on, turning one off, right? That's why the clock for NMOS is always inverted, and then you use the inverted clock for the PMOS. They're both on when you are operating that transmission gate. So that's how you can model it. And there might be a very simple problem. Calculate the time delay for the digital clock, which is the tool here with the transmission gates and inverters. Let me introduce that really quickly. Here. Inverter. So if you have VDD to the PMOS and ground to the NMOS, this is off. It's off. Right? It's not being turned on. And VDD and ground. It's not turned on. During that cycle, it's off. It's not on. But for this one, it's VDD here for the NMOS and ground here for the PMOS. So this is on. At that moment, this is passing signal through. But these two are not. So if I label this as D data, this is A, point B, what's the time delay at point A in terms compared to D? So TD of D to A, what's the capacitance involved? So here you have a half, right? And because it's always on, so these are involved. So this is half of cox P, this is half of cox N. What about here? There's a Miller effect, right? So we got half here and 1 here. So it's totally 3 halves. Right? So here you got 3 halves of cox P, and here we got 3 halves of cox N, right? So totally, this one is not counted, and I still couldn't get it intuitively, but this is what the textbook tells us. So whenever this is off, the parasitic capacitance is not counted because there's no current going through it. It's not charging and discharging anything. But the caps are still shorting to the ground. If you look at from this pin here, right, it's still short to the ground. So it should charge and discharge something, even though it's not going through the channel. But you know, let's just do the calculation. Because these two are off, so the caps are not counted. Okay, because it's not charging and discharging, no current going through. It's like a disconnect circuit. Just think about it that way. Hopefully that helps.
If both of those are
It's just going here, right? Just going through here, but not going here, not going here. Just that's it. That's what's happening. Okay, so from D to A, the C total is, or CA, the capacitance that A here becomes 2 times cox N plus cox P, right? Just adding all of them together, assuming they have the same sizes. From A to B, here, what do we have here for the output as the output of the inverter? It's cox P and cox N. Yeah, nothing here. So you got input here as well. And for the input, this is 3/2 of cox P and 3/2 of cox N. So this is 5/2. CB equals 5/2 of cox N plus cox P. You are saying, hey, is there no current going through this guy? But why you are counting these caps into the calculation? Yeah, couldn't tell intuitively, but this is how it's being used, how it's being treated in from the book. Right? But the point here is to know what are these capacitance. The ones have mirror effects and the ones doesn't have mirror effect. You know what are they? You know, if you don't add it to the overall delay, you just don't add it. But you know what are these? For the inverter input of the inverter is 3/2, right? For the output is 1 times of cox, and for the input here is 3/2, and for the transmission gate is only 1/2. That's the whole point. So know what are the caps. Okay. So when you do the calculation, D2A is this, A2B is this. What about D2B? You have to calculate separately. Because the signal from here to here is not being inverted. So if you are calculating, for example, D2B, like TPHL from D2B, so you are looking at B, right, from H to L. Then here must be L to H. So it becomes TPLH of D2A, right, plus TPHL from A to B. Any questions?
Oh, I guess it would matter because of the input.
Yeah. So the delay from here to here, if you are looking at high to low, it must be a low to high here, right? And then the delay here, adding high to low to that delay. So it becomes D2B's time delay of H to L, right? High to low.
For the transmission gate, then the resistance, we just use the parallel resistance, right?
Yeah, because
so
there's no
matter if it's going low to higher, high to low.
It doesn't matter. You're right. They're just equal. Mm-hmm.
If there's a different gate there.
Yeah. Let's write it down here. So from D to A, right? Low to high, it's always going through that parallel resistor. So this equals 0.7 Rn in parallel with Rp of the transmission gate times, and there's no resistance involved from the input, right? Because it's a gate. Okay, and times Ca. Ca is here. All right, plus 0.7 times, what's the resistance involved? It's blocked, it's off, so there's no resistance here. So the input, no resistance, just this guy, right? High to low is Rn of the inverter, and times Cb. Cb. Okay. So what about TPLH from D to B? Yeah, it's TPHL from D to A. A plus TPLH from A to B, which equals the same for the first one, 0.7 times Rn in parallel with Rp times Ca plus 0.7 times Rp times Cb. Right? I think the homework assignment asks you guys to, let's see, what is in there? I think just build this D flip-flop and simulate it. Yes. So a few terms can be very confusing. So for example, SRAM, DRAM, SDRAM, flash, or EEPROM. I'm not 100% sure, but I think these are pretty much the same. But you know, the technology has been evolved so quickly, so the term changes. For example, the ROM, read-only memory, is not read-only anymore. So it's programmable ROM. What? you're writing a ROM? Yeah. Yeah. So I think they're becoming interchangeable nowadays. And flash requires 20 volts to how it stores charges. You know, it has 2 gates. It's just one single transistor can hold a charge. So it apply a 20 volts here. We don't have the time to show all the circuits and how it is being written, being read, and being programmed. But the main goal, principle of operating a flash memory is to apply a relatively higher voltage compared to 5 volts, right? On the board, usually the digital circuits. But they have a charge pump. Very similar to the charge pump compared to the sample and hold circuit we used, providing a double VDD, right? They just needed several stages to pump the charges, pump the voltage up until it's reaching like 20 volts sometimes, for example, for the 5 volts logic. So 20 volts is able to tunnel these electrons, because if you use 5 volts, electrons are being attracted to the channel, right? But if it's 20 volts, the electrons are going to tunnel to the first gate in the middle. It's so strong. Electric fields will take them out from the channel, and they will tunnel through to the being stored in the gate.
Is there anything in between
Yeah, dielectric material.
Okay, but then if the charge somehow goes, doesn't that arc it then? Wouldn't it arc?
It might be, but in a nano level.
But if it arcs, then it's going to put a hole in the oxide and it makes the.
Oh no! I don't think that happens that way. It probably just because the oxide, yes, it's an insulator. It's not a conductor, but it also has electrons, right? You don't need too much electrons. It's probably just that all the electrons are just migrating. They just move. For the flash memory, they may have to modify the oxide here a little bit. I don't know what the material is being used. But yes, if they apply a 20, but for the regular NMOS, only can handle 5 volts or 8 volts. If you apply 20 volts, it's gonna break it, it's gonna fry it. But this is definitely a different material. Okay, so it's gonna attract the electrons to the gate in the middle and hold the charges there. The charge will stay there. The flash memory is being used where? Do you know that? It's not in the 5 nanometer. No, the USB drive, the thumb drive. So the different memories are being used for different. So different memories are being used in different places. That's why I'm talking about that right now. I'm not a memory guy, but SD cards, the same thing, right? will be shifted here to 3 volts if it was like 1 volt, for example. And if you program it, which means you apply 20 volts to the gate, you programmed it, okay? So the charge will be trapped in the middle gate, and then it requires more voltage to turn it on. Does that make sense? Okay, so the threshold voltage will be 3 volts instead of 1 volt. That's how it makes a difference. Okay, so if you apply a voltage here like 20 volts, it's a high voltage, but it's going to draw all the light chunks. I didn't plan to cover flash, but I don't know why we are here. Anyway, so the electrons are going to be attracted by the anode of the 20 volts, right? And including all these electrons as well. So they are going back and leaving all the holes there. So don't need a voltage, but the hose is like a voltage to turn it on. So it's going to be on all the time, which means the threshold voltage is like negative. You know what I mean? Like negative 1 volt, which is threshold voltage. Because 0 volt will keep it on. That's why I have to make it negative enough to turn it off. Make sense? It's called erasing. So you can make a change. That's how you memorize the different states by changing this, right? So whenever you apply 0 volts, you apply 0 volts. If it's being programmed, 0 volts is not going to turn it on. But if it's an erased cell, memory cell, it's going to turn it on. That's how it's making a difference. That's memorize 1 and 0s. Program is you apply 20 volts. You apply 20 volts, attract the electrons and trap there. So it's being programmed. You're changing the threshold voltage to a pretty high one. Yeah. Okay, so we have to cover SRAM. So SRAM. So DRAM is being used as RAM cards, right? You plug in the cards, the computer. These are cheaper. SD, no, graphic cards are something else, digital circuits. So SDRAM is not SRAM. It's DRAM. It's a different type of DRAM. So SD is a synchronous double-digit. No. SD. Oh, maybe, I don't know, actually. It shouldn't be that. Synchronous dynamic SD, right? SD, RAM, random access memory. SRAM is static RAM. It's different. Static RAM. It's being used as a cache for the CPU. You learn cache in computer architecture, right? You haven't, but yeah, it's just it's fast, but it's expensive. That's why it's not being used here, because you have so many cells in there. For the cache is usually tiny. It's okay to use a cheap one, but it's fast. Yeah, more transistors in there. So the SRAM cell. And here's the word line. It's just selection from the decoder. And these are the bit lines. So this is the bit bar. This is bit. That's when you read and write, that's a bit. And then here you have to use a circuit to make a floating VDD. So these are VDDs, and here's a clock. How that works, you have to make a floating VDD here first. So these are PMOSs that are connected to VDDs, right? So whenever you turn it on, what's gonna happen? You turn that gate on, turn this on. So current is gonna flow through and charge this up, right? Charge the 2 points up, okay? And then you turn it off. So they are getting a floating VDD here. Floating VDD. Make sense? Okay. For example, it stores a 1, 0 at the very beginning from the writing process. We're not introducing that right now, but it stores a 1, 0 on here and here. And when the word line comes, when you have 1 here, it turns these two on. This two NMOS is on, and you are trying to read it. I'm talking about the reading process, right? It's a reading process. I'm trying to read this 1 here to this line. If I pre-charge this to VDD and now I turn it off, it's become the floating VDD. If I read it, what I'm gonna read from here? It's a 1, 1 across the 2 terms of the NMOS. It's not changing anything. It's still 1. So I'm gonna read the VDD here. If it was 0, 1 previously stored here, what's gonna happen? Is this 0 strong or not, or floating? No, it's on. Why is this strong? Why? Because this is 1, right? 1 means this is on, this is 0, right? Wait. 1. Wait. Oh, the circuit is wrong. Sorry. Yeah. Yeah, like that. Make sense? Yeah, it's just the same circuit as the latch. If I have a 1, 0, for example, okay, then is this 1 a strong 1 or weak 1? Or floating 1? Strong 1, because 0, 0. There's no difference as this, it's just a latch we just saw, right? Yeah. If I got a 1, 0 here, 0, 1 here, is this 0 a strong 0 or a floating 0? It's a strong 0 because 1 is here, this is on. Okay, come back here. I pre-charge these 2 nodes to VDD all the time. Doesn't matter if it's stores of 0 or 1, 1, 0, doesn't matter. I pre-charge it to VDD, okay? I'm gonna let you know why. If I had 0, 1 pre-stored here, I'm trying to read a 0 here, but I got a floating VDD. Does that matter? Why? Strong 0 and NMOS is good at? Yeah, so it's gonna discharge the floating VDD to here. I'm making this node to be a 0, strong, weak. Strong. So you are reading a 1 here, a 0 here. Make sense? If you had a 1, 0 instead, what's gonna happen? When the word line comes, the decoder turns this on, 2 NMOS on. Don't look at this one yet. It's gonna be inverted because it's a latch. It's positive feedback. Whenever you got a 1 here, you got a 0, 0, 1. Right? We don't care about bit bar right now, just bit. We're reading bit. So if you had 1, 0 on the 2 sides, but it pre-charged to VDD, and it becomes a floating VDD. And the 1, 1 on the two sides of the nodes, which are going to read here. No, get a 1, 1 is there's no voltage drop. It's not discharging or charging. It's just like two voltages. It's going to make this point to be a strong 1, but there's no current because they have the same voltage. Okay, so that's how you read it. So you can read it. That's how you read a SRAM cell. And next, so on Friday, yes, we will have a presentation, but I will go through the writing process of the SRAM so you can do the homework, right? And we are done after that. So on Friday, we'll go through the writing process of the SRAM first, and then let you guys present your results.
Oh, man. Basically, come tomorrow, right? What?